So the first problem is design a reinforced concrete beam with balanced stress reinforced that will resist a bending moment of 140 kN meter, assuming D is equals to 1.5, B, FC is equals to 12 MPa, Fs is equals to 160 MPa, and N is equals to 8. So the first one that we have to determine is what will be the width of the beam. The next one is what is the value of the moment arm. And the last one is what will be the steel area required. In order to solve the problem, we first have to determine D given. So the first given is D is equals to 1.P that was assumed in our problem, and FC is equals to MPa, Fs is equals to 160 megapascal, N is equals to 8. And our bending moment is equals to 140 kilonewton meter. So the first problem is to determine the width of the beam. So in order to begin our solution, we can use this formula, which is the formula of the bending moment, which is also given in our problem. So the formula of the bending moment is equal to 1/2 times Fc times B times Kd times T times JD. So in this formula, we are able to derive it, resulting into a BD squared is equal to MC over 1/2 times FC times K times J. So in our problem, MC is given, D squared was assumed as 1.5 times B, and FC is also given. However, this K and J is unknown. So let's find first the K, which is the ratio of the distance to the neutral axis, and J, which is the ratio of the distance from the center of compression. The K, which is the ratio of the distance to the neutral axis, we can use this formula, Fc over Fs over M plus Fc is equal to 12 MPa over 160 over 8 plus 2, resulting as K is equal to 0.375. And in finding J, we can use this formula, which is 1 minus 1/3 K equals to 1 minus 1/3 times our K here, 0.375, resulting as J is equal to 0.875. Since we already found K and J, which is K is equal to 0.375 and J is equals to 0.875, so recalling our derived formula from the formula of the bending moment, we have this BD squared is equal to MC over 1/2 times FC times K times J, resulting as 140,000 Newton meter, which is what we have observed that 140 kilonewton meter from the given was converted into 140,000 to make it only as Newton meter. And we have divided it into 1/2 times 12 times 10 to the power of 6 times 0.375 times 0.875, which are our K and J, resulting a value of BD squared is equal to 71.11 times 10 to the power of 6 cubic millimeter. We already get the BD squared is equal to 71.11 times 10 to the power of 6 cubic millimeter. Since we only have to find the B, which is the width of the beam, we have to substitute the given or the assumed given D, which is equal to 1.5B. So we substitute this 1.5B to this D squared. So resulting a B times 1.5B to the power of 2 is equal to 71 times 10 to the power of 6. In order to calculate the B, we have divided it into 1.5 squared. So 1.5 squared will be cancelled there, and also we have to divide also in the right side 1.5 to the power of 2. So resulting this So we can cancel the root of 3 or cube root. So the remaining is only b, resulting is cube root of 71.11 times 10 to the power of 6 divided by 1.5 to the power of 2, and we can get 316.2 millimeter. So the second problem, or the second one that we have to find, is the value of the moment r, which is also denoted as JD. So the formula of JD is equal to our D minus 1/3 times KD. Since we didn't found the D, so we have to find first the D, which is equal to D equals to 1.5 times P. So we all know that our P is 316.2 millimeter. So resulting D is equals to 474.3 millimeter. So substituting it to our formula, which is equal to JD is equal to 474.3 minus 1/3 times 0.375, which is our K, times D, our D 474.3 millimeter, result in 415.01 millimeter. So letter C, the question is, what will be the steel area required? So we can use this formula, which is also another formula of bending moment, which is equal to Fs times As times JD, and we can derive it in terms of As, which is equal to our bending moment over the Fs times JD, is equal to 140,000 Newton meter times our Fs 160 times 10 to the power of 6 times 0.41501, which is our JD, that we had converted it into meter, in terms of meter, because our unit of 140 and 160 is also meter, resulting as As is equal to 2.11 times 10 to the power of negative 3 m squared, is or equal to 2,110 millimeter squared. So let's move on to our second problem. So the second problem is a rectangular beam having a width of 300 millimeter and an effective depth of 600 millimeter is designed to be reinforced for tension only if F prime C is equal to 27.50 MPa and Fy is equal to 413.70 MPa. What is the balance ratio? What is the maximum allowable steel ratio? And what is the maximum steel area required? So first, let's move on to our given. So from the problem, our given are B is equals to 300 millimeter and D is our effective depth is equal to 600 millimeter, and our F prime C is equal to 27.50 millimeter. In connection with our beta 1 is equal to 0.85, since our F prime C is less than 30 MPa and our Fy is equal to 413.70 MPa. So, letter A, what is the balance reinforce ratio? So, we have to find the balance reinforce ratio. And we all know that this problem is a doubly reinforced beam. So, we can use this formula, which is the balance reinforce ratio is equal to 0.85 times F prime C times our beta times 600 divided by Fy times 600 plus Fy is equal to 0.85 our Fc times our Fc is equal to 27.50 MPa times 0.85 times 600 times our Fy, which is equal to 413.70 MPa times 600 plus 413.70 MPa, resulting PB or our balance reinforced ratio is equal to 0.028. So, the next thing that we have to find or our B is what is the maximum allowable ratio. So, we have this formula, P max is equal to 0.75 times PB is equal to, since in our first problem, which is to find the balance reinforced ratio, we got a result of 0.028. So substituting it to this formula, we can get P max is equal to 0.021. So the last thing that we need to find in the second problem is to find the maximum steel area required. Since we already get our P max, which is equal to 0.021, we can substitute it from the formula of the maximum steel area required is equal to P max times BD, which is equal to 0.021 times our B, which is 300, times our D, which is 600 millimeter, resulting AS max is equal to 3,780 millimeter squared.